Hello, welcome again. We are solving GATE 2020 Aerospace Engineering paper. Question number 45 is for a general aviation airplane with tail efficiency xi is equal to 0.95, horizontal tail volume ratio VH is equal to 0.453, downwash angle slope d epsilon by d alpha is equal to 0.35, wing lift curve slope CL alpha wing is equal to 4.8 per radian, horizontal tail lift curve slope CL alpha tail is equal to 4.4 radian per radian, shift in neutral point location as a percentage of mean aerodynamic chord is round off to 2 decimal place. Okay, so shift in neutral point per unit aerodynamic chord is given by, so this is neutral point per unit chord HN. HN is location of neutral point per unit chord, and this is the aerodynamic center per unit chord. Okay, so due to this, the shift in neutral point is per unit chord is HN minus HAC WB wing body. Okay, so that is equal to VH. VH means that volume ratio, horizontal tail volume ratio. AT means this uh, tail lift curve slope, that is 4.4 per radian. A means wing body lift curve slope 4.8 radian, and this psi is your efficiency, tail efficiency. Okay, and this curly sorry epsilon, curly epsilon by curly alpha is downward slope, downward central slope. Okay, so that is 0.35. Okay, so putting these values we can get HN minus HAC wing body as 0.25641 or 25.641%. Okay, so that is 24 point, so 25.641%. Okay. Next, question number 46. A single engine propeller driven general aviation airplane is flying in cruise at sea level condition. Density of air at sea level is 1.225 kilogram per meter cube with speed to cover the maximum range. Okay, for drag coefficient CD is equal to 0.025 plus 0.049 CL square, and wing loading W by S is equal to 9844 Newton per meter square. The speed of airplane is dash meter per second, round off to 1 decimal place. So CD is equal to 0.025 plus 0.049 CL square. Okay, so that is CD. And for maximum range, we have that CL 1 by 2 by CD should be maximum. Okay, or CD by CL 1 by 2 should be minimum. Okay, so this is the so this equation can be converted into this by dividing CL 1 by 2 and then differentiating with respect to CL and then putting it equal to 0. So if we put it equal to 0, then we get CL as 0.4123. Okay, so 0.4123. Okay, now the speed is in general is given as 2 W by rho infinity S by CL, and CL we will take corresponding to this, and W by S is given as wing loading per unit area, that is 9844 Newton per meter square, and rho infinity is 1.225 kilogram per meter cube. So putting these values we can get velocity as 197.43 meter per second, but in the answer key the answer is given as 149 to 151.0. So that is corresponding to maximum endurance. So the paper certainly get wrong uh, wrong word here. That should be maximum endurance. For maximum range, this should be maximum. Okay, and the corresponding velocity is this 197.43 meter per second. Okay. Next, the design flight Mach number of an ideal ramjet is engine is 2.8. The stagnation temperature of air at the exit of the combustor is 2400 Kelvin. Assuming specific heat ratio of 1.4 and gas constant of 287 joules per kilogram per degree Kelvin. The velocity of air at the exit of the engine is dash meter per second, round up to 1 decimal place. So the temperature ratio of ramming across ram and across ramming and across that nozzle should be same if we consider the isentropic expansion and we consider the same substances, same fluid flowing in the ramming portion and in the nozzle portion. It means no fuel has been added or the fuel added has been neglected. Okay, so the temperature ratio across ramming is given by 1 plus 1 gamma minus 1 by 2 m square, so where m is your Mach number. Okay, and so that temperature ratio is equal to temperature across combustor, sorry, across nozzle. So this is T0C is your stagnation temperature at the outlet of combustor, because fuel has been so because heat has been added, so that temperature will be different from this. And T is your exit temperature of nozzle and T is your ambient temperature. So that temperature ratio is across ramming process and that temperature ratio is across nozzle, and this temperature is given at 2400 and this is T, and M is given as 2.8, Mach number is given as 2.8. So from this we can get T here 934.579 Kelvin. Now we have T naught or T naught C, it means the temperature at the inlet of the nozzle, and we have T, that is temperature at the exit of the nozzle. So from the energy equation we can find out velocity at the exit, so that is V square by 2 Cp T naught by T, or putting the values of T naught, T and Cp, we can find out V at it. That is 17162.244 meter per second. Okay, next, the operating condition of an aircraft combustor are as follows. The rate of total enthalpy of air entering the combustor is equal to 28.94 megajoule per second. The rate of total enthalpy of air leaving the combustor is equal to 115.42 megajoule per second. Mass flow rate of air is equal to 32 kilogram per second. Air to fuel mass ratio 15.6. Lower heating value of the fuel is equal to 46 megajoule per kg. The efficiency of the combustor is dash percent round of to 2 decimal. So the mass flow rate of air is 32 kilogram per second, and air to fuel mass ratio is here 15.6. So the mass flow rate of fuel is 32 by 15.6, 2.05 kilogram per second, and so that is the mass of fuel flowing per second. And combustor efficiency change in enthalpy, because enthalpy that is the enthalpy at the exit of the combustor per second, and that is the enthalpy at the exit of the combustor per second. So the change in enthalpy of the in the burning process divided by the heat supplied by fuel. So heat supplied by fuel is your change in enthalpy is your this quantity, and heat supplied by only the fuel, that is 2.05 into 46, that is 0.97170 or 91.7%. So answer is 91.7%.